Hello. Today we will be talking about the collapse of the Silver Bridge and why it failed. The Point Pleasant Bridge, nicknamed the Silver Bridge, was a two-eye-bar suspension bridge that opened in 1928, which connected the small communities of Point Pleasant, West Virginia, and Gallipolis, Ohio. The bridge collapsed 39 years later on December 15, 1967, killing 46 people during the evening rush hour. It remains the deadliest road bridge collapse in American history. So what went wrong? After a thorough investigation, it was found that 1/8-inch manufacturing flaw in eyebar number 330 was the culprit. The propagation of this fracture and failure of this eyebar will be discussed in detail in the next few slides. Eyebar number 330 experienced high levels of fatigue up to the point of failure. Fatigue is a form of failure that occurs in structures subjected to dynamic and fluctuating stresses, often resulting in a brittle fracture, even in normally ductile material. Fatigue causes failure to occur at stress levels much lower than the designated yield or tensile stress of a static load. The stress level just before reaching this failure point is called the fatigue limit. A fatigue limit for bridge materials, often steel, ranges from 35 to 60% of the tensile strength. In the case of the Silver Bridge, it was made of a newly invented, high-strength, heat-treated medium carbon steel that had an ultimate tensile strength of 105,000 psi. This puts its fatigue limit between 36,750 psi and 63,000 psi. At the time when the bridge opened, the weight of an average car was around 1,000 pounds, but by 1939 the weight nearly tripled. This sometimes put almost 70,000 pounds of stress on the bridge at one time, a value well beyond the fatigue limit for the type of steel used on the Silver Bridge. There are three steps to fatigue failure: crack initiation, crack propagation, and final failure. Crack initiation is when a small crack forms at some high point of high stress concentration. A stress concentration, also known as a stress razor, is a small internal or surface flaw or a structural discontinuity at which an applied tensile stress will be amplified and from which cracks may propagate. Points of discontinuity include holes, grooves, notches, and pivots. In the case with the steel eye bar, the point of high stress concentration was at the inner edge of the eye hole. This type of stress concentration results in a crack that is perpendicular to the applied stress load, as shown in the red arrows. Crack propagation was advanced by additional corrosion fatigue, a type of failure that results from simultaneous action of cyclic stresses and chemical attacks. Eyebar 330 suffered from rusting from water getting trapped between the eye hole and the pin, as well as peelings from nearby factories and automobiles. Fretting and pitting from movements in the joints in response to changing loads encouraged further degradation. The corrosion coupled with poor bridge design resulted in the eyebar having an abnormal amount of stress on it. The crack eventually made its way to the outer edge of the eyebar, resulting in a brittle fracture on the side where the crack first started, as indicated by the smooth break in the picture, and hence some ductile fracturing on the opposite side, as indicated by the jagged edge in the picture. And hence, elongation of the eye hole also occurred, resulting in a 4.5-inch gap when the eyebar was pieced back together for examination. It was found that the head of the eyebar was loaded with 3 times the amount of stress as other parts of the bridge, which could explain the amount of elongation in the eye hole and why the eyebar also had hints of ductile fracturing. The high strength, relatively high carbon content, and heat treatment of the eyebar steel results in more acidic microstructure, giving the highest hardenability and strength, but very low ductility. Hence, this microstructure helped facilitate the brittle crack propagation of the eyebar up to the point where it starts to fail. Once the eyebar failed, it caused a force imbalance that the bridge was not designed for. Hence, once one piece of the bridge broke, the whole bridge went into total failure and collapsed, as seen here. In the aftermath of the Silver Bridge collapse, President Johnson set up a standardized national bridge inspection program, making it mandatory to inspect all U.S. bridges every 2 years. Road improvements could also have been made, such as additional anti-corrosives to the steel, strengthening the bridge by adding more eye-bar members, and using heat treatment such as tempering so that ductility is not fully lost in the steel.